yk minus 1 plus yk minus 2 over 2. That's it, right? Okay. Does anyone want to give this a shot? And I'll guide you through it if you have any questions. Like Evan, who was asking questions about one of these two? Brian? No?
I would.
You would? Want to give it a shot?
Just the block diagram?
Yeah. So we'll make x come in from the left. So what has he done here? For each of the for k, there's no delay. For the x to the k minus 1, there's a single delay. Then what's the negative 1 do in front of it?
Inverts it.
Yeah, it's a negative because it's negative up in the difference equation. For the k minus 3, there are how many delays?
3.
3 delays. So he has the 3 D boxes there, and he has a 2 in front of it to give it the right coefficient. And so what is he doing with these? The y is the output, so he's got a little feedback on each one of them. One with a negative 1/3 and one with a negative 1/2. And generally those terms there, as long as they're not greater than 1, will result in a system that doesn't blow up on you. But that doesn't matter in this case.
The coefficient of y?
Yeah, they're the ones, the feedback ones are the ones that cause it to have poles outside of the unit circle.
Oh.
The poles from all that stuff on the left, all of those are at the origin essentially, unless you have other feedback like that. Now, there is a lot of redundancy here. Let me see if you can see that this is exactly the same thing. Here's x of k. Which one have I done now? I've done the one with the most d's. But instead of putting the coefficient in front, I put it in the back. Why? Yeah. So I can do this. And then I've got one with 1 delay. What is the 1 delay? The 1 is negative 1. Now, in these digital ones, we don't typically put negative signs here. We have them within these little coefficient circles kind of things. And that's very commonly how it's done with the delays in the boxes and the coefficients in circles for the digital. This guy over here can be taken the same way. The maximum number of the delays is 2. So we do the delays first. So we can pick off anything else that's less. Let's see, 1/2, is that right? Yeah, 1/2. And then we can pick off, let's see, a single delay.
Negative 1/3.
Negative 1/3. Now that's the correct direct implementation, but we haven't learned the various implementations. So whatever you do that will work will be fine. So his answer would have been fine. This answer is slightly better because it requires less steps. less hardware if you're doing it in hardware. There is actually even a better implementation, which is the minimal implementation, which is shown on, in Botson's book somewhere on one of those pages. But we never learned the various implementations, so any implementation would be fine. Now, what if you needed to turn this into a Z transform? Let's take this a step further and turn it into a Z transform. So a Z transform would be like an H of Z, which is a Y of Z over an X of Z. So first thing we need to do is take that difference equation and turn it into a Z transform. So for the first term up there, I get a 3x to the Z. Since it's x of k, x of z is its transform. I didn't say what it was, just put it in there. Okay? Minus, what do I do for this term right here? Yeah. We can do this in one of two ways. We can say z to the minus 1 times x of z, because what does z to the minus 1 mean? A delay. Now, if this block diagram were shown this way, oops, y of z, I guess, then these probably would have been like this, instead of delays. However, going back to this, plus 2, let's see, z to the minus 3 x of z minus 1/3 z to the minus 1 y of z plus 1/2 z to the minus 2 y of z. So how do I turn that into this form here?
Equal sign or other y of z.
Yeah, what do I want to do? Collect all the y of z terms on one side of the equation and all of the x of z terms on the other side of the equation. All the x of z terms are already on, where is the equal sign?
You don't have it.
Ah,
It's not an equation.
It's the purple way.
it's the purple up there.
Very well.
Yeah.
That's why I switched.
It's the purple up there because y of k was equal to that. There should have been this. Blame it on Jim. So the x of z's are already on one side of the equation. We're going to leave this piece totally alone. What are we going to do with the other 3 pieces? So, being lazy, so when I bring the 1/3 from this side of the equation to that side, what does it become? So is it legal to write that this way? Yeah. And what's this term become when I move it to the other side of the equation? Next step. What is the next step?
Factor and divide.
Factor out the y of z.
And the z, x of z.
What do I get?
1
1
plus 1/3 c.
or this. Either way. Minus, oh goodness, 2 and z. There, how about that? So I I factor out the y of z on this side. If I factor out the x of z, what do I get? First term is
3 minus 1.
next. And this is exactly what you would do in Laplace transforms as well, you know, for something like that. So again, it's so similar. I can ask you a question like this, and it's just like asking one in terms of Laplace, except for these z to the minuses and stuff. So what do we do now? Y over z, or y over x, is, I move the x over here. What do I do with all of this stuff?
Down there.
Disregard it.
Be my guest. That'll make it easy to grade. Third, z to the minus 1. Minus 1/2. Z to the minus 2. And typically what we'll do at this stage is one more step. Take the highest order or the lowest order, however you count that. Like that. And then what will we end up with? 3z cubed minus 1z squared plus 2 divided by z cubed plus 1/3 z squared minus 1/2 z. Notice that these terms here come from the feedback here. So if they didn't exist, all my poles would be where?
Outside?
No,
At the origin. The origin. So if you just have a system that feeds forward and doesn't have any feedback, you don't generally have anything but poles at the origin. These difference equations. All right, this is the best way to do it. Can I figure out where the poles are? Where are the poles? One at the origin, and then what else? Think of the rest of it as z squared plus 1/3 z minus 1/2. Does this mean it's not DIBO stable? Would it mean that if they were s's instead of z's?
Yeah,
Yes,
definitely.
but it's different for z's. So what do we have to do to figure out if this transfer function is BIBO stable?
Find,
Yeah.
find the.
So we have to figure out where those are, which means probably put them in a quadratic equation. So the other two poles are negative 1/3 plus or minus the square root of 1/9 minus 4 times, so plus 4 times 1/2 over 2. Did I do that right? Doesn't feel right. Yeah, it is right. So that's 2 and 1/9. Don't have a clue what that comes out to be. 2 and 1/9 plus or minus like that over 2. I have no idea. It's a little over 2. What's the square root of a little over 2? About 1.5, roughly.
Yeah, 1.45.
What's it? 1.45?
Yes.
So it's 1/3, negative 1/3 plus or minus 1.45 divided by 2. Throw that in real quick. Where are the two poles?
Well, I saw the negative 0.89 and 0.559.
Negative or positive 0.459?
Positive.
459?
No, 559. 559.
5, 5, 5, 5, 5.
Something like that?
5, 5. Mine. Not the 4.